Let's practice with a triple integral. First of all, apologies for my squeaky chair. Hear that? I swapped my fixed desk chair for one that rocks a little bit, and when it rocks, it squeaks a lot, and I'm too lazy to go move it back right now, so we'll just have to deal with it. I just recorded the optimization example video, the one with the absolute extremes, and there is a lot of creaking noise going on in the background of that video. I'll try to minimize it here. But anyway, we're going to set up a triple integral that will find the volume of a solid region. It's a region that lies under a plane, x plus y plus z equals 9, and then whose projection is given with boundaries down in the xy plane. So the three-dimensional shape that we're talking about is a plane. You can see from the equation of the plane that the intercept on every axis is just 9. When x and y are both 0, you get z equals 9, right there. When x and z are both 0, you get y equals 9, right there. And similarly for x. So I'm going to do my best to, let's see. Okay, that's not great, but I guess you can kind of see that plane right there. So it's kind of a flat tent perched over the xy plane. Now down here in the xy plane, there's going to be a region that's carved out by those equations that I've drawn really badly right there, because I'm going to flip up the x and y axes so we can see the xy plane on its own and see what these two boundaries need to look like. Now, one of them is given in a bit of a strange configuration. This problem comes out of the open source textbook that I have posted in Blackboard. And so they set it up this way. We're going to work with it. This is a weird way to write it. That curve is also known as x squared equals y minus 1, or y equals x squared plus 1. And so we have a parabola as one of the boundaries of this region in the xy plane. That was my attempt to draw it right up there. We also have x plus y equals 7. That's just a straight line with intercepts of 7 in both directions. So there we go. And so, oh, and I forgot x equals 0 as well. That's just right here. So this is the region in the xy plane, which is the basement of the thing whose volume we're going to find up there. So it's this standing column with a basement that looks like this, and it goes up until we hit that plane, so it will have a slanted roof. And we want to find the volume of this thing. Well, when you're using triple integrals to calculate a volume, what we're going to do is build up this. A triple integral over the full region E of 1 dv. That gives us the volume of the region in question. So what we have to do is describe all the bounds of this region in the 3 coordinate directions. So we need to unpack dv, and remember it could be dz, dy, dx, dx, dy, dz. It can come in a whole bunch of different ways, and we'll figure out which is simplest. I think we'll save z for last, because I'm pretty sure we're going to do z first. All right, it ran out of space. There we go. Because the equation of the plane is given as x plus y plus z is 9. The basement of our solid is down on the xy plane, which is z equals 0. And so the upper edge is the plane solved for z. So if x plus y plus z is 9 as our plane, that's also known as z equals 9 minus x minus y. So we are going from z equals 0 up to that plane, z equals 9 minus x minus y. And then we're going to unpack the boundaries in the xy plane, which is this region. And it looks like the best way to do that is to say I'm going to design this region so that we can march out in the x direction from 0 to this point, whatever it is. But for any one of those x values, once we've picked an x value, our region starts at the parabola and ends at the line. Starts at the parabola, ends at the line. Starts at the parabola, ends at the line. So for any of these x values in the y direction, our region begins at the parabola and ends at the line. Which means that if we start at x equals 0 and march out to x equals a number to be determined later, then the region begins at the parabola, which is y equals x squared plus 1, and it goes up to the line, which is x plus y is 7, or y equals 7 minus x. Let's check the progression of information. If we were to actually start doing this integral, well, the function is just 1. So we would do the antiderivative with respect to z, plug in 0 and this, so we'd have x's and y's floating around now. We pass it along to the integral with respect to y, resolve it, and for y, plug in x squared plus 1 and 7 minus x. So by the time we get to the outer integral, the only variable left is x, and we're going to integrate x away and plug in constants and get a number back, which is what we need because we're finding a volume. A volume has to be a number. So as always, we need the limits on the outer integral to be constants, and as soon as we find out this mystery number, we will have that upper bound and be ready to go. Now, how do we find the x-coordinate of that point? Well, pardon my messiness here, I'm just going to come out here onto the side and do a little bit of scratch work. So this is not the page that I would turn in if I was writing this up as a solution to a homework problem. But we just need to find where the line intersects the parabola. So let's say we have y equals x squared plus 1. The point that that shares with the line x plus y equals 7 has a y value of 7 minus x, would be x squared plus 1. And so we would have x squared plus x, let's collect all the constants, minus 6 equals 0. Turns out that factors, which is probably why they picked this line in the first place. Turns into x plus 3, x minus 2. And that means that our two options for the x-coordinate of that point are either 2 or negative 3. We happen to know that we are on the positive side, and so this coordinate is x equals 2, which means my diagram is kind of drawn all skewed, but that's okay. And we can put that 2 right there. Now, I will leave it to you to actually execute this triple integral. Remember, at this point, you do not have to be doing them by hand. If you've gotten through this to the point where you have all the limits in all the right places, that's fine. Go to Maple, go to Wolfram Alpha, and execute the integral mechanically, not by spending another page just doing all the manipulations by hand. This is the good stuff, getting all the limits in the right places.